Now, another phenomena that we will learn a little bit about is the reflection of sound waves that are called echo. Echoes are a process in which sound encountering a surface is reflected or returned. And one of the properties of the echoes is that the angle of incidence of the sound wave onto a surface relative, well, to the surface that you see right here, the angle of incidence is equal to the angle of reflection. So when sound waves hit a wall, it acts like a mirror. The mirror reflects the light waves, walls will reflect a sound wave, and so the angle at which it hits the wall will be the same as the angle at which it comes off. Similarly, if the sound wave were being directed directly at the wall at 90 degrees, which would be perpendicular to the wall, then the sound wave would be reflected straight back at us. But in any case, what you can see here is that that the person listening, that the what we now call acoustics of the room can be either good acoustics or bad acoustics. So good acoustics are ones in which we minimize the echoes, that we basically attenuate the echoes so that they do not interfere with the sound that we're listening to. In this particular case, the speaker is generating a direct sound wave that goes from the speaker to the listener, but there are other sound waves that hit the walls and bounce over to the listener that produce these echoes, and this can cause a distortion or a delay of some of the signals to overlap with signals that are being produced much later. So this sort of echo pattern is a very detrimental source. We would like to attenuate it as much as possible so that when we're listening in a room that we don't have these echoes occur. Some animals make very strong, easy, and profound use of echoes. It's called sonar, or sound navigation and ranging. We now know that a number of different types of animals use this to locate or to visualize, they don't visualize it, but to locate by hearing what the distance is to an object that they're approaching. And what their brains are doing is measuring the time between the sound emission and the echo, and that tells them how far away the object is. So by measuring the time between the emission and the echo, then we can not only determine this, but in particular, if that echo time is very short, or we get the reverberation very shortly after the sound, we know the object is close. It hasn't traveled a far distance. But if the object or the sound, if the echo occurs at a much later time, we know that the object is further from us. So this echo, the time between the sound emission and the echo, can tell us how far away an object is. Very important. Another place where echoes become extremely important is in use of reflection of sound is in medical ultrasound imaging. Reflections of ultrasound waves from organ surfaces are responsible for giving us some very nice images of what's occurring inside of a patient. Most people are familiar with the fact that ultrasound can be used to show the outlines and contours of a newborn fetus or a fetus or a baby before birth. And basically what happens is that the device sends high frequency sounds into the body and reflects the waves more strongly from the boundary between the organs. So if you are going from a boundary of low density fluid to high density fluid, there will be a reflection of the sound. And by measuring the echo time for each ray of sound from the source, we can tell how far away that boundary is from the device doing the measurement. And here you can see the center of these circular rings would be somewhere above the figure where I'm pointing to, and by measuring the reflected sound waves and the time, we can find how far away is the interface between low density and high density from the source of the wave. So ultrasounds are very nice tools for using the reflection of sound at the interface between high and low density materials in the body and generating images from them. Concert hall acoustics. A concert hall adds reflectors at strategic points to carry sound to the entire hall. Must avoid reflectors that cancel the sound echoes from two or more directions, which are called dead zones. And absorbers are placed at strategic locations to absorb unwanted echoes. So you can see here that there are reflectors on the ceiling to reflect the sound waves in a way that give us a constructive interference of the waves at the location, so that we can carry the signal much further throughout the concert hall. Now, here's a phenomena that's talked about in your textbook a little bit, and that is to do with the temperature dependence of the velocity of sound. The author talks about going camping as a youth and observing that if there were people far away across the lake, that he could holler over to them much more effectively at the nighttime than he could during a warm summer day. The reason was that as he observes, is that cool air forming over the surface of the lake will produce what's called a temperature inversion, which we talked about in the thermodynamics chapter, where we get cool air below and warm air above. And this often happens at over lakes, particularly in the summertime, in the night air, when we get a cool layer of air over the water and a much warmer temperature air on the surface at the shorelines of the lake. So this observer here is yelling in his megaphone, and he sees that, or understands that, he's able to transmit that sound over this lake much more effectively at night than he has during the daytime. So what is going on here? Well, what he is doing effectively is making use of the fact that the sound waves get bent downward if you have warm air above cool air. So you remember that the starting out from the horn, or the point where the source of sound is, the crests of the compression waves are relatively flat vertical lines. But what happens as you go further over the lake is that the cooler air here has a slower velocity than the warmer air above it. So the line of compressions which forms the crest of the sound wave, begins to bend downward, and the bugler now reaches the ear of the dog very effectively. On the other hand, if we have cold air above the warm air, the sound wave gets transmitted in an upward direction, and the observer at the other side of the lake was not able to hear the sound nearly as well. So cool air above warm air does not allow large transmission distances. Warm air above cool air does allow us to hear sounds, and this is why the camper by the lake is able to communicate with another camper very far away on the other side of the lake much more effectively at nighttime than at daytime. So that was an example of the refraction of sound due to the temperature dependence of the speed. We're going to conclude this chapter with the study of resonances and forced vibrations. So we're going to talk a little bit about that right now. And we'll go through a couple examples. Forced vibrations, first of all, we want to set up vibrations in an object by a vibrating force. So plucking a strings on an instrument will set up vibrations on an object by a vibrating force, so that's a forced vibration. Forcing air through a flute or horn or organ pipe, the wind instruments, those are all forced vibrations. If you have wind gusts that hit a bridge from the side, you can actually create very damaging effects where if the wind gusts occur at the right frequency, the bridge will oscillate and eventually collapse. So these are all examples of forced vibrations that we have. Now, there's something which we talked about before, which was called the natural frequency of the vibration. It usually consists of one unique frequency or set of frequencies. An example of the natural vibration or frequency is a pendulum swinging back and forth. Does not matter how much you change the amplitude or the disturbance of a pendulum or an object oscillating on the end of the string, no matter how much you pull it down to start with, it will oscillate at the same frequency. Now, guitar, and that's because it depends only on the length of the object and the length of the pendulum and the mass at the end. But, or I'm sorry, I said that wrong. It depends only on the length of the pendulum and the acceleration of gravity. It doesn't depend on how I initially start those oscillations. Now, guitar strings do also have natural fundamental frequencies of oscillation. One of them, or one way we can define a frequency, is the velocity of the wave divided by the wavelength. So you remember that we've said earlier that the speed of a wave, which in this case is sound, which in this case is 330 meters per second, and is going to be the same for all wavelengths, not just one, is equal to the frequency times the wavelength. So if the frequency times the wavelength is a constant, that means that as the frequency increases, the wavelength goes down, and vice versa. Guitar strings have what we call a fundamental frequency of oscillation, which is also a natural frequency, given by the speed of those waves traveling back and forth along the string. So these are the ones that produce the standing waves. That is the velocity of the wave on the string, and the wavelength is equal to 2L. So the natural fundamental frequency of oscillation is given by, and F, by the way, F is the tension in the string, and U denotes the mass or mass density of the string that's being plucked. Higher harmonics, which are to say those other frequencies that also give us natural vibrations or standing waves, are any multiple n of that fundamental frequency. So for whatever fundamental frequency I have for a string, there will be multiples of those, which are also natural frequencies. They are producing standing waves on a string, and can have a multiple. But the natural fundamental is the lowest frequency that the string can have, which is fixed at both ends. The higher harmonics can occur for strings with more with some frequency that's a integer multiple of the fundamental. So if a string has a natural frequency of 500 hertz, then it can that string will also produce frequencies at 1,000 hertz, 1,500 hertz, 2,000 hertz, 2,500 hertz. Any multiple of 500 hertz will also be produced by the string. Whereas a tuning fork, for example, only have a natural frequency at one value. They don't have multiples. There is only one natural frequency. And these natural frequencies are given by certain circumstances that we've talked about in nature. For the pendulum, for the swinging bridge, an object oscillating on the end of a string, which is connected to a spring. Should say an object oscillating on the end of a spring might have been a better statement here, which oscillates up and down as we showed in chapter 19. So a phenomena in which the frequency of force vibrations matches the object's natural frequency will cause an increased amplitude of motion. So, for example, if I have a child that's on a swing and I have a parent that is standing on either side of the child, and the parent on the left side or behind the child hits him with a certain force to accelerate him on the swing, and the other parent on the other side gives a pulse down, a force down when the child is returning on the swing, that will be giving an external force that matches the natural frequency. That is to say, the frequency of the parents hitting the child matches the natural frequency of the child on the swing. And then we see that the amplitude of the child begins to swing higher. Pushing his child on a swing at her natural frequency, that will increase their amplitude. That's a resonance. The applied frequency of the force matches the natural frequency of the object that's responding. Shaking a rope at the fundamental frequency of the rope, that produces these standing waves that we talked about, and I can have a standing wave with the fundamental frequency or a multiple of the fundamental frequency, all of which will be natural frequencies for the rope. And by shaking the rope at the fundamental frequencies, or twice that frequency, or 3 times that frequency, we can double or increase further the amplitude of the wave. So a resonance, we're amplifying the effect of the displacement. Troops marching in rhythm with a natural vertical oscillation frequency of a bridge, digging their heels in hard, in unison. This will produce a large vertical force that will obviously cause extreme damage. Now, we can imagine let's consider a case where we have two tuning forks, one at the left end and one of the column and one on the right end. So imagine there's an identical tuning fork on each end of this column. Then if I strike the tuning fork on the left, causing it to oscillate or vibrate, it will send a compression sequence of air down the tube, as we've talked about before, but then the tuning fork on the other end will receive those compressions at exactly the same frequency that it is designed to resonate at or designed to oscillate at. So when we do that, we can actually hear sound coming from the tuning fork at the other end when we produce the vibration on the first tuning fork. It transmits its frequency through the air, and it's picked up. If, on the other hand, I have the wrong tuning fork there and it does not oscillate at that natural frequency, then the tuning fork that I use on this end will not produce any sound on the tuning fork on the other end. This is what we call matching or resonances. A tuning fork on the right that vibrates at different natural frequency from the one on the left will not vibrate. That's an important feature of what we talk about in these sine waves. Now, there's another example of interference of sound waves that occurs quite frequently, and that is when we have two sources of sound that are vibrating at different frequencies. This periodic we observe when we have these two frequencies present close together that are slightly out of sync. That is to say that the frequency of one tuning fork might be 400 cycles per second and the frequency of the other is 445. The difference in the frequencies is 5 hertz or 5 compressions per second. That's another way of thinking about hertz, by the way. It's the number of compressions per second that is hitting your ear. So 5 hertz means 5 compressions per second. What is observed and what is explained by these two sounding pitching forks, I guess you call them pitchforks. Must be another word for them. Sounding forks, we'll call them, at slightly different frequencies, is that occasionally there will be a lineup of the constructive compressions of air molecules of one with compression of air molecules with the other. But it only occurs at the difference frequency. So if this one is producing 440 compressions per second and this one is producing 445, the lineup or the agreement, the time intervals between which you get perfect lineup between the compressed airs of one fork and the compressed airs of the other is only 5 times per second, not 400. So it's at a much lower frequency, and it's given by the difference of the two tuning forks. So this is obviously, or not obviously, but this is how the tuning fork is used for tuning a piano, for example. The piano tuner has his own tuning fork. He strikes it, he hears that, he hits the key, and he listens for this wah, 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 this slow variation in minimum amplitudes, which we call the beat frequency. And then he tightens the string until those slow periodic variations in intensity have disappeared. And they disappear when the frequency of the tuning fork is exactly the same as the frequency of the piano string, which is adjusted by tightening it. So when that occurs, the beat frequency goes away. F1 is equal to F2, so there's no frequency of loud, soft, loud at this low frequency, and we can use that to actually tune instruments. The applications, we've talked about the one with the piano, the tuning instruments in orchestra by listening for beats between instruments and the piano tone. So for example, if we know that one violin is already been tuned perfectly, the second violin player can strike his strings and listen for the beat frequency and then tighten it until the frequency of his neighbor's string and the frequency of his own string is exactly the same. Reverberation. So this gets back to, we're switching gears a little bit, but perhaps a little bit out of order. This was actually back to the reflection of sound, and the question is, when are the reverberations most easily heard when you sing in the room? And in other words, would you expect to hear those echoes when you are in a room with carpeted walls, hard surface walls, or open windows? Well, in order, it turns out, as many of you have observed, that when you put carpet on the walls, you absorb the sound. It reduces the reflection, so the reverberations will occur best when you have hard surface walls, and the reflected signals will be more noticeable. Okay, so I think that, let's see if we've got any more. That's the end of the chapter. We'll stop there and resume on chapter 21. Thank you.